This is a talk on the 7 women who changed astronomy, and I just want to quickly mention, without being too political, I just found out 2 days ago that NASA and the Vera Rubin Telescope, amongst other federal agencies, have been told to take down any websites that mention women in STEM or any kind of thing that has any kind of DEI or women reference. So I think this talk comes at a very good time. I've been a mentor and a teacher and had interns for many years, and all my teachers and interns are of all backgrounds and genders. So I hope this talk embraces that. And I also want to say that why did I pick 7 women? It's because we only have like 50 minutes. There are countless numbers, and at the end of this talk, I will show as many names as I can. You won't be able to read them, but when we do the recording, you can go back and look at them. But there's way more women than the 7, but these 7 are special to me. So we're going to start with Hypatia. Hypatia, we're talking 370 to 415 CE, Common Era. Philosopher, astronomer, mathematician, born in Egypt in Alexandria. At the time, it was a flourishing mecca of intelligence and everything. Part of the Roman Empire. She's remembered for designing and teaching about astrolabes, but we're going to talk about astrolabes. And it was mostly her pupil that we found this out, his writings. And if you notice her birth and death date are CE, Common Era, it would have been very insulting to put AD, because AD is a Christian term, Anno Domini, after Christ, and she was murdered by a Christian mob. So out of respect, we put CE with her birth and death date, not AD. And there, this was considered the beginning of Alexandria's decline, was the murder of Hypatia. So what's an astrolabe? Well, in quick terms, it's an early sextant or quadrant, right? I could spend an entire talk just talking about astrolabes, but I won't. The concept goes back to the Roman Empire. It was claimed to be invented by her, but maybe not. Let's see something here. It's older than that, and we have some proof of that. It's more likely that Hypatia was an expert in teaching about it, and the earliest known treatise on it is actually about her father. So it's possible her father invented it. So we're not sure. But she was definitely an expert on it and taught about it. It's basically a planisphere with a moving part. And the word planisphere is interesting. It's basically planarizing a sphere or flattening a sphere. It's a projection of the heavens onto a flat piece of something. And once again, people aren't really sure. People attribute the planisphere to Hipparchus. But then again, we have no proof of this. So the history is a little mucky back then. There's not a whole lot of, proof of these things, but we're getting closer. And then through the years, astrolabes got better. There's one from 694 AH, and that's another form that's a Arabic form of the date, or 1294 CE, which is the same as AD. And then they found one under a rock someplace, literally, on Valentia Island, from 1588, and that one's a little different. If you notice, it's got a heavier part here. Like this one maybe is all kind of the same weight. Maybe it's even wrong because it's heavier on top. This one's heavier on the bottom, so that when you hold it, you maintain a vertical, similar to a sextant or a quadrant. And this is how you use one. There's the steps. You basically take the rete and you rotate it to point to a star. And then you use the planisphere in the background to line up with dates and times, and based on using the information on the planisphere behind it and the actual star on the rete, and the back planisphere is called the mater, you get the time of day, basically, the date and time from this. So very similar to a sextant or a quadrant. And here's some more steps. So basically, let's just say you can see the star Deneb. You point your astrolabe rete at Deneb, and then you rotate until Deneb on the astrolabe, it's there, lines up to where it's supposed to be, and then you read off the date and time. So that's the astrolabe. So we're going to go to the next person, because like I said, we only have 50 minutes, and there's 7 of these people. Caroline Herschel. We're jumping now to many years later, 1,000 years later or more. Um, Her most significant contributions and discoveries of comets, including the periodic comet 35P Herschel and Rigollet. She was the younger sister of William Herschel, with whom she worked out with her career. She was the first woman to receive a salary as a scientist and the first woman in England to hold a government position. First woman to publish scientific findings in the Philosophical Transactions of the Royal Society, and awarded a gold medal by the Royal Astronomical Society, and to be named an honorary member of the Royal Astronomical Society in 1835. So she's kind of the first of the first. She's recognized as a contributor to science as a woman, which was not that popular back then. She was the first. And there's more. She contracted typhus at the age of 10, and this stunted her growth. She only grew to 4'3". She was a little person, and her mother didn't want her to be, continuing in education. She wanted her to, manage the house. But in 1772, her brother William took her to England, where she established herself as a teacher of music. So originally, Herschel, the brother and sister, were music people. And she was a singer, a good singer. But he tutored her in mathematics, and eventually they gave their last performance in 1782. And from that point on, William Herschel, after discovering the planet Uranus, became the court astronomer to George III. And that's how she, basically got hooked onto, astronomy. And it's interesting because this is true. In winter nights, when the ink froze upon her pen, she was still by his side. That's one of the stories, is she's outside with William Herschel taking notes, and it's so cold out that the ink is freezing in her pen. Oops, I gotta get back to that. Uh-oh, I can't advance. What happened? Where'd my advance? Oh, there it is. It came back. Good. She discovered 8 comets. She discovered several nebulae and star clusters. She presented to the Royal Society an index to John Flamsteed's observations, together with a catalog of 560 stars that were emitted, and basically fixing up things. She arranged 2,500 nebulae and star clusters into zones of similar polar distances, so that her nephew John could re-examine them systematically, and the list was eventually named the New General Catalog, and today we all know many NGC objects, of which 5,000 of them were the Herschels, pretty much. This is my favorite of hers. She discovered what they now call Caroline's Rose Cluster, NGC 7789. It's an open cluster in Cassiopeia. She discovered it in 1783. It's found among the rich fields of the Milky Way. So even though it's a nice dense cluster, it's dense around it too. The stars around it are pretty dense. This really is one of my favorite, either binocular or telescope or photographic objects. It was formed about 1.6 billion years ago and 50 light years across. And it's about the size of a full moon. It's a pretty big star cluster. It's magnitude 6.7, so it's kind of faint, but I kind of like that it's kind of faint. But beautiful object in a binocular or telescope. And that's a picture I took of it. Next, anti-jump cannon. Now we're going to get into a little more sciencey stuff, which is good. We're talking late 1800s, early 1900s, American astronomer, whose cataloging work was instrumental in the development of contemporary stellar classification. And so this is like another woman I added in. So this is like 7+ or 8, is Wilhelmina Fleming and Edward Pickering, a man. She worked with them and credited with the creation of the Harvard classification scheme, which was the first serious attempt to organize and classify stars based on their temperatures and spectral types. And there's another interesting thing. So, Caroline Herschel had the typhus disease and was 4'3". Annie Jump Cameron got scarlet fever and was deaf throughout her career. So not only are they battling like a sort of gender biased profession, but they have other handicaps too that are holding them back, that didn't hold them back at all. So this is interesting about stellar classification. I just bring this up because a lot of people have it wrong. Thanks to Delta Fawcett, people think blue is cold and red is hot. Incorrect. Blue is hot, red is cold. Let's remember that, not forget it. Okay. So this has to do with spectroscopic study of stars. So this is, I like to say that the telescope was the first thing to change astronomy, but the spectroscope was the second and maybe bigger thing to change astronomy. So if you don't know how a spectroscope works, you basically put a slit someplace, either in the front or the back of the scope, to get the light down to like a narrow, line. And then you use either a prism or diffraction grating, in this case, it's a diffraction grating shown, to split the light into its colors, into its, component wavelengths. And then you have a detector, which is in this case probably a film camera, because they were using glass plates back then. And that's how you get spectral pictures of stars. And this is an example of one. This is the one at the Lick Observatory in 1898, and it's got a big, a slit and a spectroscope and a diffraction grating. And Keeler and John Brashear built that one. So Wilhelmina Fleming, she's sort of the first person that did this, decided to use the absorption lines of hydrogen to place the spectra into different classes, because hydrogen is an abundant element, which we didn't know at this time, by the way, but she picked a good one. She picked hydrogen. I mean, they had a suspicion it was abundant, but not as much as we know now. And she made the strongest lines A and the next strongest B and worked her way down to O, where the lines were almost invisible. And here's a sample. And then Annie Jump Cannon noticed that this arrangement almost put the stars in order by temperature. And as measured by the continuum of the spectrum and by photometric colors, she switched O to the front, and she's the one that came with this "Oh, be a fine girl, kiss me." This is a mnemonic to remember the class of stars, which are O, B, A, F, G, K, and M, with, O being the hottest and M being the coolest. So this is what Annie Jump Cannon did. And then what I want to show you is that it wasn't as easy as that made it look. I mean, this is the photographic plate they got. They got a bunch of little smudges. So these are the slits from the spectroscope, and every star goes through that slit. So every star gets this little smudge of spectroscope in black and white, right? So don't forget, this is 1893 using plate film. And then she looked at it and had to, using a microscope on the plate, had to figure out, what lines were prominent and which ones became less and less and less. And this is Annie Jump Cannon's contribution to astronomy, is she came up with a spectral class of stars based on temperature. So this is huge. This is a big thing, that we now have stars classified by how hot or cold or in between they are. And then I show a little thing on the bottom. If you don't know the lines of hydrogen, this is called the Balmer series. But, it goes from H alpha to H gamma and, and further, H epsilon. H epsilon is the last one, which is roughly 656 nanometers, which is, cool, up to 397, roughly 400 nanometers. So these are the spectral lines of hydrogen that are, true of hydrogen everywhere in the universe. I mean, this is one of these concepts that is interesting, is that we assume what happens in a laboratory by heating up hydrogen in a gas tube is the same everywhere in the universe, because if it's not, we're in trouble, right? So this is sort of a big assumption, that everything that happens on our desks and labs here is the same everywhere in the universe, and hydrogen should be the same everywhere in the universe. So that's Annie Jump Cannon. So now we're going to do Henrietta Swan Leavitt, also an American astronomer, and she was into Cepheid variable stars. She also faced a lot of gender-based obstacles, and she joined Harvard Observatory as what they called a computer in those days, right? These were women that were hired to do, repetitive math and these observations and things. And meticulous analysis of stellar photometry, the light from stars, led to the discovery of a star whose period luminosity change is a function of its actual brightness, right? So by correlating the period of the variability of the Cepheids with their intrinsic luminosity, in other words, how bright they really are, astronomers can now use that to tell how far they are using the inverse square law, right? So if you know how bright something really is, and you know how dim it got, you know how far it is. So this is a big deal. So before this, the way we found the distance to stars is with something called parallax, right? It's basically, you hold your finger out and you close one eye and you close the other eye and you see it jump back and forth, and that distance, or the angle that it moves, is a proportion of the distance it is from your eye and the space between your eyes, right? So it's basically the base of a right triangle. Not basically, it is. It's the base of a right triangle. And so based on the angle and the known base, you can get the distance. That's only good for so far, though, right? So parallax today gets us out, maybe to here, maybe 100 million light years if we're lucky, and that's today. Back then, it was way less. They didn't have the resolution in telescopes and stuff we have now. But then Cepheid variables get you further. Cepheid variables get you to other galaxies, thanks to Henrietta. And then further than that, we use supernovae, but that was past Henrietta's time. So Edwin Hubble took advantage of this. He realized that in Andromeda Galaxy, he found a Cepheid variable, and then knowing it was a Cepheid variable, figured out its apparent brightness, and from that, figured out its actual, its distance, and realized Andromeda Galaxy is really far away. And then he used a thing called redshift. So redshift is, astronomers love naming things in simple words. It's simply how far things shift to the red when they're moving away from you, right? This is from the Doppler effect. Something moving away from you has its frequency shifted to a lower frequency. So all these lines of hydrogen, which are sort of sacred and like a fingerprint of hydrogen, shift in a certain amount, and by that shift, he could calculate their velocity. So combining their distance and velocity for as many Cepheid variables and as many galaxies as he could see, he came up with what we now call the Hubble constant, right? This is that the velocity is a function of the Hubble constant times its distance, right? So it's a straight line, roughly. He basically created a straight line of velocity versus distance. And if you flip that around, you do simple math, you do d is v over h, what it does is it eliminates the need to find the distances anymore. All you have to do is find the redshift and you've got the distance, because if this is a straight line, from this point on, once you know what the slope of the straight line is, you can always get a distance. So this really opened up the doors in astronomy. People were able to just look at redshifts, which is pretty easy compared to all these other techniques, and you could immediately get the distance of some other thing. And we use now, astronomers all over, even today, use redshift as a distance measurement. And then it gets even more interesting. This is getting out of sight outside the talk of women in astronomy, but in 2011, Perlmutter, Schmidt, and Rees realized not only is the universe expanding, but it might be accelerating. And I say might be because, it's still not 100% confirmed, but pretty much sure it is. This is the actual data, you can see the difference between accelerating, decelerating, and constant. Very small little differences, so you need really good data. But they were using supernovae, not Cepheid variables. So using supernovae, they've determined that the trend is that the universe is accelerating in its expansion. And that's weird because the laws of physics don't allow that. If you throw a baseball, think of the Big Bang and all the galaxies are now expanding, unless you add more energy, you can't violate the conservation of energy. Unless more energy is added, the final velocity cannot be greater than the initial velocity. At best, it can be equal, but not greater. 1/2 mv squared initial equals 1/2 mv squared final. So this is what is now known as dark energy. There's some energy that we can't see causing the universe to expand. So if you ever hear the term dark energy, it's not that the energy is dark, it's that there's energy we can't detect in any wavelength, radio to, gamma. We don't know what it is. So this is, so Henrietta Leavitt sort of started this, this whole thing about the universe expanding and now accelerating. So now we go to Cecilia Payne-Gaposchkin. This ties back, by the way, to the anti-jump cannon, but you'll see in a second. So during the anti-jump cannon years, so this is just a little bit later, people assumed that if you saw a spectral emission of a star and you saw more lines of nitrogen or more lines of sodium or more lines of calcium, that the star had more of that. But Cecilia Payne said no. She said, so this is what scientists thought, that if you see like sodium and you see magnesium and you see strong lines, that means that there's way more of that element in that star. And that's kind of like common sense thinking. But common sense thinking doesn't work in physics, because common sense makes me think that heavier objects should fall faster and all that other kind of stuff. That's wrong. That the Earth is the center of the universe is what my common sense says when I go outside and look at the stars. But she thought outside the box. And she began to work at Harvard trying to calculate how much stuff is in each star. And this is not easy. This was painstaking work. First, she developed a way to quantify the intensity of the absorption line. So you got to make that, quantifiable. You can't just go by, what you see with your eyes. And then she spent a year working pretty much day and night, analyzing the spectra of hundreds of stars, trying to develop some principles for these observations. And after 2 years, she built a temperature scale for stars versus the absorption intensities. And but basically what she figured out is that they all had the same composition, right? If you use this method of sort of, temperature versus composition versus, line intensity, that all the stars are pretty much made mostly of hydrogen and some helium, and the rest is almost zero. And the fact that so many stars have identical spectra itself suggests this uniformity of composition. Unfortunately, though, her bosses at the time, Russell and Shapley, said, no, that's impossible. So she was going to make these claims in her PhD, but they told her not to. They discouraged her from doing that. So the idea that the stars are made of hydrogen, helium, and very little else seemed bizarre. And she'd used a method nobody had used before. So it took a while for astronomers to come to terms with this idea. It was a major paradigm shift, but eventually they did. Astronomers began building their theories around the fact that stars are mainly hydrogen. And today we know that 91% of the atoms in our own sun are hydrogen, 8.87% are helium, and the remaining is 0.13%. So this is Cecilia Payne's great contribution to astronomy, is that all stars are made of the same stuff, and their spectral lines is really just the temperature. Vera Rubin, of course, one of my favorites, because I worked on the camera for her telescope, the telescope named after her for 10 years. And there's a picture of her as a young woman at the Lowell Observatory in Flagstaff. It looks like they're loading a cold camera or a film plate into a cold camera in 1965. So her and Kent Ford at the Carnegie Institute in Washington in the 70s were looking at punch cards. And these are punch cards that had Doppler shift from the Andromeda galaxy. In other words, they're looking at the spiral arms of Andromeda galaxy, and part of the galaxy is rotating away and another part is rotating towards. And they looked at all the, stars of the Doppler shift, not really the stars, but the portions of the galaxy. And it seemed like the edges were moving just as fast as the stuff near the center. And to them, this was very strange because this kind of disobeys, Kepler's laws and Newton's laws about rotation. And I like her quote. She says, in a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but we're only in about third grade. So we're going to talk about dark matter. Of course, we have to. We talked about dark energy. So does anyone know what dark matter is? Well, the good thing is nobody knows. This is sort of a Tim Tate tongue-in-cheek Venn diagram of all the accepted theories on dark matter. We're talking peer-reviewed, not crackpot ideas, and some are within other ones, and supersymmetry and extra dimensions and modified Newtonian gravitation, etc. So this is how I like to explain what dark matter is. Imagine you're two very evolved fish at the bottom of the ocean, and you've just built your first really good telescope, and the first thing you look at is a flag on Earth, terra firma. And it's moving, and it's waving. What's making that flag move? I don't see anything. And the other fish says, well, I think it's air. And the fish says, air? What's air? I don't know what air is. He says, oh, we think it's a third phase of matter. And the other fish says, what do you mean? It's not just solid and liquid. There's another phase of matter. He's like, yeah, we think it's a gas, air, and it's making the flag move, but we can't see it. So that's dark matter. There's something making the galaxy do what's on the right and not what's on the left, which is what Newtonian and Kepler mechanics would say. And we can't see what's doing it. If you include the mass of all the stars and even leave room for the fact that maybe there's a bunch of, particles and asteroids and planets and stuff that you can't see, it doesn't even come close to predicting what we see. So these galaxies are moving by something that we can't see and we can't detect. It's the air to the fish. It's dark matter to the humans. And you look at our own solar system. Our own solar system shows no evidence of dark matter. Pluto is going a lot slower than Mercury, and it follows Kepler's laws perfectly. But our galaxy doesn't match that curve. In fact, it might even be possible that the outer parts of our galaxy are going even faster, and not the same as the inner parts. So this is sort of the dilemma right now is we don't know what's causing this. And Vera Rubin was one of the first people to, discover this. And, for people that don't know, Vera Rubin is going to be the largest survey telescope in the world. It's going to have the largest digital camera ever built. It is going to be on a mountain in Chile, in the Cerro Pachon Ridge. It's only at 7,500 feet altitude, which I was a little disappointed. I wanted it to be higher, but they didn't ask for my opinion. And there's Calypso. Calypso is interesting. Vera Rubin is not adaptive optics, but Calypso will actually send like sodium lasers and stuff like that and analyze the atmosphere. And they're going to kind of do an after the fact adaptive optics corrections to Vera Rubin's data using Calypso data. So it's after the fact adaptive optics. And then that's the camera that the Vera Rubin telescope has that we worked on at Brookhaven National Laboratory right here on Long Island, New York. And the focal plane. So there's the focal plane of the camera. It's got 189 CCDs. Each CCD is $100,000. So do the math. That's $18.9 million in just the CCDs. And it's huge. It's a big camera. They call these things rafts because they look like rafts. There's 21 of them. And that's what forms the focal plane. So to test it, they took a pinhole projection of Vera Rubin, taken from an old photograph, and then used the camera to take a picture of that because a pinhole projection has no aberrations. So they use that. And I just like to show this because they did it of the people that worked on the camera too. And there I am. So there's me in the pinhole projection. There's Justine Haupt, also a Long Islander, Bill Wall, Paul O'Connor, all Long Islanders, Brookhaven Lab people. Sven, we're the people that built the camera. And I just want to particularly talk about gravitational lensing because it's a weird thing. When you're trying to find dark matter, one way to find it is to see how things really far out are being lensed. So what's interesting is gravity does bend light. And Sir Arthur Eddington led an expedition in 1919, total eclipse of the sun, to prove this. And basically they looked at stars sort of before and after the eclipse to see if the sun had an effect on their position in the sky. And they actually got a couple of stars in the sky that they could see. And they proved that the star's light passing our sun did get bent. So then you say, wait a minute, but photons have zero mass. How can gravity affect something that has zero mass? Well, Galileo proved this a long time ago. The rate that an object is accelerated is independent of its mass, even if its mass is zero, right? There's no correlation to mass and acceleration. It's so the better way to look at it is it's not mass, it's how fast something is going in gravity. So if something is going slow, they're going to get bent a lot, and something going a little faster will get bent less, and something going really fast, like the speed of light, will get bent less, but not zero. It still gets bent. It's just not the acceleration of the massive object is not affecting it as much because it has so much initial velocity. So don't think of it as gravity as a force, because it's not, it's an acceleration. Think of it that gravity bends the road that light or anything is traveling. It's sort of this space-time dip, and gravity is now bending that road, whether you're a satellite or an asteroid or light. And so Vera Rubin, what they're going to do is they're going to look at these sort of star clusters near and far and see what kind of bending they get of these galaxies and determine where dark matter might reside. Because we don't know what dark matter is, but our first step is to find where it is. So the first mission of Vera Rubin is to find where dark matter is in the universe, because it's not uniformly distributed by any stretch, which seems to be mostly on the outsides of galaxies, but this will help determine that. And I don't know if you know, but the Vera Rubin telescope used to be called LSST, used to be called the Dark Matter Telescope, way back when it was first being conceived. And last but not least, Jocelyn Bell Burnell, still alive, still with us, only one of the 7 that's still with us that I've talked about tonight. Dame Susan Jocelyn Burnell, born in 1943, so she's pretty old now. She's from Northern Ireland, postgraduate student, discovered the first radio pulsars. Discovery eventually earned the Nobel Prize, but she wasn't one of the recipients, but that's not that unusual. She was president of the Royal Astronomical Society, so that's a big deal in England, from 2002 to 2004. President of the Institute of Physics from 2008 to 2010, and the interim president of the Institute following the death of her successor, Marshall Stoneham. She was chancellor of the University of Dundee from 2018 to 2023. And in 2018, she was awarded the Special Breakthrough Prize in Fundamental Physics. Following the announcement of the award, she decided to use the $3 million prize money to establish a fund to help female, minority, and refugee students to become research physicists. And the fund is administered by the Institute of Physics. So what a generous person. She got $3 million and gave it away for other females and minorities. On November 28th, 1967, she detected what a bit of scruff, is English sort of terminology, on her chart recorder papers that tracked across the sky, right? So they got this chart recorder. Don't forget, this is 1967. They got a little, strip chart with the needle moving for different frequencies or intensities that they hear, so to speak, in a radio telescope. Then it took her months to go through this, and she established that the signal was pulsing with some exact regularity, about one pulse every 1/3 second, so like 3 hertz. They initially called this Little Green Man 1, because don't forget, 1950s, 60s, people are still into this, Little Green Men and Orson Welles and all that stuff. And basically now is now identified as a rapidly rotating neutron star. So a neutron star is a star that's collapsed, but has a very strong magnetic field, and the rotation of the magnetic field sends out a electromagnetic radiation signal, radio, and we happen to be in line with it, so we pick it up. And this is the very first radio pulsar ever discovered in 1967, and got some other people a Nobel Prize. And then as I promised, here in alphabetical order, or with some names repeated, are women that have made great contributions to astronomy, and the list goes on. That's why I didn't want people to think that I only think there's 7 good women in astronomy. There's many, many. They've all done amazing things. And I said, when we do the recording, or I can share my slides after I give my talk at Rockland, you can go through all the names, and there's quite a bit. And see right on the top, Henrietta Swan Leavitt, and so on. So into the Z's. And that's the end. Any questions?